Hi, my name is Matt Gaska. I'm an engineer with Siemens in the U.S. working with Siemens numeric CNC controls. This is a set of videos I've put together on how to compensate a CNC controlled machine tool. The target audience for this is maintenance staff and technicians at a machine builder. This is designed for people out there with grease on their hands that work with the machine every day. This is not designed solely for commissioning engineers. There's a pretty basic skill set required to be able to follow this. You need to be able to edit part programs. You don't have to write them. I'm going to give most of them to you. But you need to be able to edit them. You need to be able to run a part program. You need to be able to manipulate machine data. You need to be able to make archives. And you need to be able to restore archives. That's about it. So we're going to start with the theory of how comp works. Then we're going to take a machine tool, which has never been comped, apply comp to it for the first time to show how data in the different registers is handled, how we access the data, how the data is stored, how the control interprets it, and how we can modify it. We'll do this for linear axes, and we'll do it for rotary axes. We will also do a simple example of a squareness comp, which can very easily be turned into straightness comp if desired. Because these are my videos and I get to do what I want, we're doing them in metric. I'm going to cover how we convert this to inch, because that's a practical requirement in the US. We're also going to talk about the practical case of when you have a machine tool that's been running for a year and it's due for its annual recalibration. How do you go to the control? How do you evaluate where the data is stored, in what tables, and make the decisions of how you're going to load data back on top of something that's already been working? Generally speaking, everything that I'm going to talk about here works on pretty much any numeric control since 2000. There are some limitations because not all the controls have every function. For example, some of the economy level controls do not have squareness comp. At the end, we'll go through a chart of what works on what controls and what the software options required are. Wherever you're watching this video from, you should have seen a link for a zip file. The zip file is going to include a couple things like this presentation, some Excel files, and some part programs. In general, now would be a very good time to stop and hit pause if you don't have the zip file already. Go get the zip file and work along with me as I'm modifying the files. I hope this is helpful to you. Before we start talking about how we compensate a machine, the first thing we need to think about is what characteristics of a machine can be compensated and what machines are good candidates for being comped. Now, we have to talk about accuracy versus repeatability. Accuracy means that the machine is doing what it's supposed to be doing. It's going to the positions that we've told it to go to over an average number of times. Repeatability means that it does exactly the same thing every single time. If we look at the lower left corner, that's an example using an archery target with a grouping of arrows that are repeatable but inaccurate. They do the same thing every time, but they're not where they're supposed to be. We can shift it to the right a little bit, we can shift it down a little bit, and we can make it accurate. Accurate meaning that the spread of arrows is centered around the center of the target. Now, if we look at the upper right, that's an example of non-repeatable but accurate. It's accurate because the spread of arrows is centered around the center of the target like it's supposed to be. The problem is that the repeatability is low, therefore the spread is too large. Some people will call repeatability precision. The words are basically interchangeable. If we're looking at a machine like the upper right, where we're non-repeatable but accurate, there isn't a comp value that we can apply that will improve the centering of those arrows and get all of them close to the target. If we shift them up some, or if we shift them down, or we shift them left or right, we're never going to get much better than we already are on average. If we look to the upper left corner, that's an example of a non-repeatable but inaccurate machine. That basically can't be comped. Neither of the non-repeatable examples can have comp applied and expect good results. You may get some improvement, but you have to have a repeatable machine. Now, how do we define what's repeatable and what's not repeatable? We have to look at the data that's being collected from the lasers and other metrology devices to just find what can we expect out of a machine. Instead of talking about archery targets, we're going to talk about accuracy and repeatability in terms of real data from some machine somewhere in the US. The x-axis of this plot is the length of travel along the axis, so roughly minus 600 millimeter to roughly positive 1400 millimeter, or minus 2 foot to roughly positive 5 foot. And the displacement in the y-axis goes from roughly minus 10 micron to roughly about 170 micron, or about minus half a thou to about plus 7 thou, give or take. So this was 3 bidirectional runs or 6 runs total, depending how you choose to count. The blue lines being the positive runs, the red lines being the negative runs. Now, what we can see in the upper right corner that's interesting is that it's not repeatable through this section. In this middle section, from roughly maybe 700 to 1,000, we're pretty repeatable, but we've got a big spread here. This is interesting that we have the positive and negative run each time overlapping very, very well, but the individual sets of runs don't match. So if we apply a comp value, let's say we apply a comp value which is perfect for this middle point. If we apply that, we'll say that that's 160 micron. So I apply a comp value 160 micron of that. If we get a test run which is exactly the same as our middle run again, comps out beautifully. If I apply 160 micron of comp to my bottom line, then I get a negative value when I run this for verification. I've applied too much comp. And if I look at my top one, I've applied too little. This is the problem with repeatability. When the machine isn't repeatable, the best accuracy we can hope for overall is going to end up being based on the repeatability. Now, what's even more interesting with this, and this is part of how things are different in the real world than if I just made up data in Excel and plopped it into a plot, is that the section from 1,000 to 1,500 millimeter, the repeatability of that looks very, very different from the areas near 0 to 500, where the positive and negative runs don't even overlap on themselves. So when we applied comp to this machine, we're going to take a look at our numbers. We've got a max deviation here, about 170 micron, min deviation being minus 12. Our total repeatability is about 25 micron. So we applied comp to this machine, and the next slide will show us the results. So after the calibration runs, we did another set of 3 or 6 verification runs, depending on how you choose to count. And the machine accuracy improved quite a bit. Our original runs had a total deviation of about 180 micron. We cut that down to about 50. The top plot here is scaled exactly the same as our calibration runs. The bottom plot is zoomed in for the sake of demonstration. So lots of good things happened. The accuracy improved overall, but we didn't get it down to 0. Why didn't we get it down to 0? Well, this is one of those cases where we have to look at individual points and look at data instead of just looking at overall numbers that the metrology software is going to kick out. Because we look at our total max and min deviation numbers and so on, it says, well, we should be able to just keep messing with numbers and make this better. Well, that's sort of true. The problem is that we have a difference in these runs compared to the original runs in terms of repeatability. If we look at the original runs, the original calibration runs on top, the range from 1,000 to 1,500 millimeter was not very repeatable. Our second set of runs, after we applied comp and corrected it, those got very repeatable. Repeatability is something that cannot be improved with compensation. So what changed on the machine, or in our laser setup, or in the physical environment that caused this repeatability to change so drastically? Did somebody close an overhead door and get rid of some wind and some air currents? We can't tell from just looking at these plots. So the point is that even though we can correct many, many good things, we're only correcting a static error. We cannot correct repeatability. We're going to look at a second axis before we get into the control implementation. This axis is much shorter than the first axis we looked at. It only has about 450 millimeters of motion available. But what's really interesting is that the repeatability is 3 micron compared to the 25 micron of the first machine. This means that when we calibrate this machine and comp out the error, we should expect pretty good results. Looking at the verification runs, I changed the scaling so we can see something interesting. We look at our total deviation, and it went from 35 micron in our calibration run down to 7 micron. That's a pretty good improvement. What's interesting, though, is that the deviation that we still have is still within roughly our repeatability. Our repeatability of the calibration run is roughly 3 micron. Here it came down to 2. We probably should be using more decimals for this example, but it's PowerPoint, so we're using enough. The point being, anytime we can get our verification runs to come in within plus or minus a unit of repeatability, we've done pretty well. Now, there are certain points on this graph, such as minus 150 millimeter, we could look at and think that why don't we just put in a little bit more comp and get that closer to 0? Or the one out on the far right at plus 25 millimeter. Why can't we lower the amount of comp that we have there? The reason is we didn't pick these numbers out of a hat. We came up with these by measuring during the compensation run. Both these points are generally within the repeatability of our compensation run. We shouldn't expect much more out of correction by the control. Now, let's say, for example, we did change the compensation value at minus 150 millimeter and add a little bit so it'd get closer to 0. That's all well and good. The problem is that we may be overcompensating because we're within the repeatability of what not only our machine can do, but also our metrology system. It's also based on the setup of our metrology system. It's based on the environment that we're in. We may be doing things that if we do enough runs, we would eventually start pushing out of that range of plus and minus 1 unit of repeatability and introducing more problems than we're correcting. We've been seeing that the accuracy of the machine is limited by the repeatability of the machine. Now, instead of just correcting the points at minus 150 and 25 like I described before, what we could be doing is we could be taking a look at our compensation runs and our verification runs, trying to figure out what's causing the difference there. Now, this may be something as simple as we need to warm up the machine and move it around a bit, or spread some lubrication around, things of that nature. Or it may be more complex or less obvious, such as there are overhead doors that are opening and closing. If those change the air currents in the area, that may change the repeatability of the system. So when it comes time to set up the laser and start measuring, we're going to have some basic things we need to know about how we're going to collect data. We're going to have to tell it where are we starting, where are we ending, and we're going to have to move the machine through some points. So for this example, I'm going to start at 0 millimeter. I'm going to end at 350 millimeter. And I'm going to move in steps of 50 millimeter. So I'm going to use a part program to move the machine through those positions. Some samples have been provided in the zip file that comes along with these videos. And then the laser is going to give us numbers, and usually this will have to come out of the metrology software somewhere, but we're just going to read them off the screen of we move to 0 millimeter, we zero the laser out, laser tells we move to 50 millimeter, the laser tells us we went to 49.9, we moved to 100, the laser tells us we moved to 100.1, and so on down the line. Now, the number that the control needs is a compensation value, which is going to be the measured value minus the target. Different metrology software outputs in different formats. Some put output in compensation format, some output in error format. They're the same thing, it's just a different sign convention. Check to make sure that your software is outputting the format that the NC expects. If not, it's easy to correct later. So, we need to get this into the control. The easiest way to get this into the control is to use a part program. The reason I like to use part programs is that it's the most universal and generic way to load comp data. Some of the newer versions of the UI have screens built in to enter comp data. Other versions have INI files that can be edited and modified. I'm not a big fan of using those because that means I have to type in numbers by hand. With part programs, I can always do some kind of copy and paste from metrology software. So for the moment, we're just going to take this trivial example of 8 points. We're going to set that up, and we're going to load some data to show just the most simple implementation possible. So I have a part program that's ready to go, and it's loaded on a file server. Now you can use the USB stick, you can use a file server, whatever mechanism you would normally use to load a part program. So I've got a file named 01_simple ENC, because ENC is the type of compensation we're using. It's a .mpf extension, and I'm going to open that in WordPad. You can use any decent text editor you like. WordPad is the best one that I have available on this system. So let's look at it. So first thing is, comment that says turn off comp before loading the comp table. We have to turn off all of our comps before we can load new data. Otherwise, we're overwriting data which is currently being used by the control. The control interprets that data as read-only and will fault. So new comp is like pressing the set MD active button in the machine data area. It does basically the same thing of set the machine data active, let the control reconfigure itself. So we told it to turn off the comp, activate it. Very good. So I've got my step value. When I moved in my steps, I was doing 50 millimeter per step. We'll look back at the drawing. Back at the drawing. Doing 50 millimeter per step. That's correct. Where did I start? What's my minimum value? I started at 0. Where did I finish? My maximum value is 350. So, at each point, starting at 0, moving in increments of 50 millimeter, I'm going to enter the comp value that I want the control to apply. So at 0, I have 0 punched in, 0 matches over here. At the first point, which is 0, my first starting point, plus 50, my step, times 1 from my first point, I got a minus 0.1, and so on down the line. So I do all 8 points. Note that the indices start counting at 0 instead of start counting at 1, but that's not too big of a deal. So when we're done, we need to turn the comp back on because we want to see it do something. We want to hit a new conf statement, which again is the activate these machine data. I just throw a message that says loaded to the header so that we can see it for the sake of being able to see that it's done. Wait for 2 seconds and end the program. So let's go ahead and give this a try. So we just created the file that's going to load all the comp data that we created for this simple example, and it's sitting on the file server, so let's go select it for execution. Again, if you're doing this off of USB stick or anything else, just pick a different method. We're just loading a part program. So I'm using Operate 4.7 Service Pack 4, which is the latest and greatest as of the recording of this video. So I go to Menu Select, Program Manager. I've got my NC files over here like normal. I've got a file server very creatively named Comp Demo over here. I hope you also have something coherently named if you're using a file server. I've got the part program we wrote named o1simple.enc. If we open it up, we can see that it's exactly what we typed in WordPad, where turn off the comp, new conf, load some data, and then we have a loaded statement at the end, followed by a dwell, followed by an end of program. So hit execute, and then I'm going to press cycle start. Program runs very quickly, which is why I like to have that loaded followed by the dwell at the top, just so that I know that it ran and I don't need to sit here and keep mashing cycle start, hoping that it runs and not knowing if it ran for sure or not because it was too quick. So let's go look at the diagnosis area and see if we can see the comp values. So go to diagnostics. Now, the top level of diagnostics is one of those things that's going to be very different depending on what version of UI you're running, especially with HMI Advanced. With HMI Advanced, the service access screen is about here somewhere. That's where you're going to be going instead of to the operate path. So, come into diagnosis area, come over to Access Diag, select that. We get the screen. I'm in simulation, so don't worry about the fact that I'm missing most of my enables. Press Service Access, and I can see all kinds of good things, like what is the position of my measuring systems. In Cinemeric, we don't call them encoders because we don't know if they're rotary encoders, we don't know if they're linear encoders. They're just measuring system 1, measuring system 2. When we get into things like linear motors where you don't have any rotary encoders at all, then they're all just scales, so we just call them measuring system 1, measuring system 2, and we don't worry about what they are. So now I'm going to try to jog my axis. So I'm jogging my axis, and it's moving. We can see the screen's updating, it's moving. I should be seeing a comp value right here. I should be seeing a number telling me how much comp is active right now. The answer is 0. Did we screw something up? Well, the control's doing exactly what it's supposed to do. This is one of those things where instead of making you watch a video where everything goes perfectly and your system never matches that, we're making some mistakes on purpose. One of the things that we didn't do is that after we changed those core values like the step size and the start point and things like that, we haven't done an NCK reset yet. Those values are not effective until you do a reboot. If we had changed just the comp values, like how much comp at each point, the new comp is good enough. The core ones, step size, start position, end position, those require an NCK reboot. So I'm going to go ahead and do that. So menu select, setup, reset. We're back from reset. I decided to cut that out and save you all some time. I figure I have better things to do than watch me reboot. So now I'll start jogging my x-axis. And this time, as promised, I get a value for how much comp do I have showing. Now, there's a few things that I'd like to show you. First, I'm going to run a different part program. I'll show you what it looks like on the file server. And what this is going to do is at each point, x50, x100, so on, I created a just an M0 and stop. And it's going to print out the position to the header. This is a very, very fancy program to do nothing particularly special. So I'll select that program. So I'm back to my diagnostic screen. The reason to show the position in the header is so that we can see where we are in the program and that we're stopped without needing to be on the main machine screen. So at 0, we have no comp as expected. At 50, we got comp of minus 0.1. If we look at the comp table we had, this all lines up perfectly. Now what I'm going to do is I'm going to stop in the middle of the next one. I'm going to slow down my feed rate, and I'm going to stop at about 75, give or take. So at 75, that's halfway between the points at 50 and 100. Halfway between 50 and 100 would be halfway between minus 0.1 and 0.1, which would be 0. For as close as I stopped to 75, I'm pretty dang close to 0. The reason this happens is that between points, the control interpolates the data linearly. So if we have these blocks don't represent the data I punched in, they just represent something I was able to draw. That as we have each point where I have something defined at 0, I have something defined at 50, I have something defined at 100, it just is a straight line between them. So whatever shape that we have, the control just automatically calculates the difference in space between the two of them, looks at the difference in comp, and weights it based on how close you are to each side. So as we go slowly past 75, we go to 0 comp, and we start pushing 0.1. Scroll off to the side a little bit. Same thing here. I'm going to go from 0.1 to minus 0.2. I'm flipping signs on purpose so that this is something somewhat interesting to watch. So it goes from a positive to a negative, and we're going to keep running straight off the end. Because if you remember right, the last point we put in, it was at 350 millimeters. So let's go, we're at 350 millimeters. Just like our program says, we should have 0.1 millimeter of comp. We're going to go ahead and drive to 400 now, which we know that we have no point for. That's off the end of our comp table. I'm going to drive out to 400. We're at 400. I have 0.1 millimeter of comp. The reason I have this is that when the control reaches the end of the comp table, either in the positive or negative direction, it just takes the last value which was applied at that point and applies that for the rest of the axis travel. This is relevant because there are conventions that had existed in the past where, let's say we had an axis that moved from minus 1 millimeter to 351 millimeter. There were conventions in the past where you needed to have a value at minus 1 and 351, otherwise you would have no comp applied between the last point in the table and that little bit extra of overshoot. That's not true in cinematic controls. We don't need to do that. Just letting it saturate based off the last known value, if you have short overshoots like that, is generally just fine and acceptable. We don't need to move right up to the end of travels. So now, as long as we're in the diagnosis area, we're going to look at something else. This number here, this shows us the active measuring system. Again, the active measuring system just being 1 and 2. Generally, measuring system 1 is the motor encoder. Generally, measuring system 2 is the direct encoder. Sometimes that's not always true, but those are special cases that we're not going to talk about. But this will give you the active measuring system number. Now, if we look at the part program we had, each one of these points, I've got the name $AA encoder comp, 0, 1, AX1 equals some value. What do all these things mean? For encoder comp, which is just the pure, we're going to apply a comp to an encoder, this is saying, are we on measuring system 1 or measuring system 2. I can have separate tables for each measuring system. If you have a machine that has scales, it's generally rare that you would bother to pitch error comp the motor encoder. Generally speaking, if you're talking about a linear axis, you have a round motor, you have direct scale, you're only going to comp the scale because you're not going to run parts with the position loop closed on your motor encoder. So this entry here tells us which comp system or which measuring system we're using. We have separate comp tables for them. The second number here, the 1, which keeps incrementing, tells us what point do we have. The third piece we have is the axis name. Now, there are many different conventions for axis names. I like to use the AX1, AX2, AX3 convention. The reason I like to use the AX1, AX2, AX3 convention is that it's the most generically applicable naming convention that works in the most cases, because there are cases where you have multi-channel machines, or axes which are passed between channels, things of that nature. You may have cases where you may have multiple x-axes in the system in different channels. There can be some complex stuff. Using this AX1, AX2 nomenclature, I know that I'm always applying to a machine axis. I know which one I'm applying it to. I have no syntax problems, and my life becomes easier. I have better things to do than guess what axis names are. I can just put in a number and be done. Now, similarly, we have the header data. Again, these are the couple that require the reboot, the step, the min, and the max. Now, there's a couple rules with these. The minimum must always be less than the maximum. If you don't, the NC throws a fault. What the system does not check, though, is it does not check that the minimum plus some multiple of the step size ends on the maximum. They don't need to end together. It's not a necessary condition. So you could create tables where, let's say we've got this table that's 0 to 350. If I had entered a step size of 51, which clearly is not going to end evenly on 350, it's going to end on 355. What'll happen is that at 350 millimeters, it's just going to saturate and run off the end, like we saw when I ran out to 400. So the system won't fault on that because it's technically not a problem. It's a strange definition. It's not really recommended. It is generally recommended to make your step size line up well with your min and your max, but it's not technically wrong, so it works. We've loaded a comp file for the x-axis, so we're going to duplicate the same data and load it for y. So I'm going to go back to my file server, take my comp file for x, rename it. You could be using any names you want here. Open it up in WordPad. I'm going to do a find replace. Replace axis 1 with x, with axis 2, which is y. Replace all. Close that. Save it to my file server. Go back to operate. Select my program. Execute. Cycle start. And it fails. Again, this is a case where it's failing intentionally. The reason it's failing is that it's telling me there's an illegal axis index on block 9. I hit program correction, select my block. It's number 9 right here. So, why is it failing? The reason it's failing is that we have not allocated any memory for the y-axis comp table. Especially in older controls, the default value for the comp table sizes was always 0, and this was done to preserve as much memory as possible for things like part programs and work offsets, things of that nature that were also going to consume memory. If the comp tables weren't going to be used, there's no reason to have them consuming memory. So in older controls, there was no memory allocated by default. In the most modern systems, the first couple axes get 128 points by default. For the sake of getting through the last demo, I threw in a couple points off screen for x-axis, so we didn't need to deal with the memory allocation first. We could just go ahead and load the table. So let's go and take a look at how we're going to allocate this memory. First, we go to machine data. Setup. Go to axis machine data. Pick axis Y, so that's what I'm working on. If we look, I very quietly put in 8 for X1 without telling you. And now I need to allocate some memory for Y. Now, this is one of those things where we need to be careful. The reason we need to be careful is that, especially on older controls, when memory allocating machine data are changed, at reboot, the machine data will allocate memory as the control boots. The problem is that it will do things like push part programs and work offsets out of memory, which means that you lose your part programs and your work offsets and your tool offsets. So there's an easy way around this. The first thing we do is we go make an archive. So setup archive, create setup archive, and all we really need is the NC data. Never hurts to have more. And I will just very creatively call this NC01. And we're done. So now I'll go change that machine data. And I'm going to give us 8 points, the same number of points we have for the x-axis. You'll also notice that we get this fault 4400. 4400 is telling us that memory is going to be reorganized. We're going to do things like lose part programs, work offsets, tool offsets. That's obviously a bad thing. So what we do is we make another archive. We're going to call this NCO2. NCO1 gets us back to our original state. NCO2 is going to have the changed machine data stored for us. So what we're going to do is that as soon as NCO2 is done being created, I'm going to read that back in immediately, because during the archive restoration process, the memory is allocated first. The part programs and work offsets are put back in far at the end, so the memory allocation problems are not a hassle. So I'm going to restore this archive, and it's being restored. And the archive's been restored, so we can say OK. Now, if we go back to the part program we'd originally run, again, these are on a file server, so they would have been protected anyway because they're not part of the NC's memory. We'll pick that file. Hit cycle start. We get our favorite message of loaded, which means we're done. Now, we know that we have to do an NCK reset, because if we don't, the header data, the step size, min, max, those are not effective. We saw that on X. So we'll just do an NCK reset. And the NCK reset is done, so let's go see our comp values being applied in the diagnosis area, just like we did for X. So we have Y selected. I'm going to select Y, and I'm going to jog it. And Y is jogging. We should be seeing comp values right here. Why are we not seeing comp values? We did the reset, like I said, we had to do. If I go out to the main machine page, my y-axis is not referenced. None of my axes are referenced. Comp does not get applied until the axes are referenced. So let me reference my axes. Very quickly done. Go back to jog. Go back to my diagnosis area. Start jogging Y. And as promised, I now get comp values applied now that I'm referenced. Because again, watching videos where everything just works for the guy running the video easily, those are boring because those don't match the real world. I'm running into problems on purpose. So Alarm 4400 can be a bit of a hassle. And for machines roughly newer than 2016, starting with software 4.7, that's been resolved, where for almost all memory allocating machine data, it's no longer a concern. I've turned that off because there's a very, very, very small percentage of machines out there with latest and greatest software compared to the number of machines that are out there running with old software. So I wanted to demonstrate how old software works. If we want to see how new software works, we go to Menu Select, Setup, General MD, search for 17950, and set that to a value of 1. Conveniently, the value of 1 is the default value, which means that in general, we pretty much don't see Alarm 4400 anymore. So we've seen how we can enter comp values from a part program. Now, typing in numbers by hand into a part program is great for trivial examples where I made up nice round numbers for an 8-point table. In the real world, we're going to be dealing with things that are not nice round numbers and way more than 8 points. So we're going to need to get used to dealing with the system variables that go with this. What I'd like to do right now is I'd like to show you where to get the manual for this if you want more information on the variables. So fire up whatever web browser you happen to have installed. Go to whatever your search engine of choice is and search for Cinemeric Extended Functions Manual. This is also available on Dock on CD. I'm not allowed to install Dock on CD on this computer, so we're going to the web. The manuals are available for free, and we're looking for the specific Extended Functions Manual. The Functions Manual are a series of 3 manuals: Basic Functions, Special Functions, Extended Functions. and their groupings of smaller manuals on different topics. So we search for the manual, we get a copy, we download it, I open that up, and as promised, this is the extended functions manual, and we can see that it's a collection of smaller manuals. The manual K3 is compensations. The manual R2 is specific to things for rotary axes. The manual W3 is specific for tool change. These are all small, discrete, singular manuals that each have a contained topic. We're going to be looking at the K3 manual for compensations. If we use the bookmarks built into the manual, we can see that there's a point where we can expand compensations, and this breaks out into smaller sections. What we care about is interpolatory compensation. If we remember from the example I did earlier with the boxes and the purple line, we could see that between each point in the comp table that we created, the control interpolates the value of that comp table. So this section 5.4 is where we're going to get most of our data. Now if we quickly look, this starts at page 265 and goes to page 314. I'm not going to read 50-some pages of manual to you. I'd just like you to see that this is here. What we're mostly looking for is what they call lead screw error and measuring system compensation. Now, depending on which region of the planet you come from, there are going to be different words for the same thing. Other than this manual, I've never heard the phrase measuring system error compensation. For talking about correcting an axis relative to its own direction of travel, some people call it pitch error compensation, some people call it lead screw comp, some people call it ball screw comp, some people even call it spindle comp. Sometimes people refer to ball screws as spindles because it's a round spinny thing, just like you have the round spindles on a banister walking up and down a flight of stairs. The information is contained in here. So if we go back to the commission example for this, it starts going through the variables that we've been seeing, like how many points are in the table, what's the minimum point, what's the maximum point, what's a step. This gives you all the syntax that you should need for these variables with an explanation. When we're compensating a machine axis, we're going to need to move the machine from some starting point to some ending point in some increment of steps. The easiest way to do this is with a part program. You can write your own, you can get one from your metrology vendor, or you can use the one that comes in the zip file, which should be associated with this video. So I've got my zip file on my file server, and compensation-enc. I'm going to open that up. Windows is trying to protect me from my own file. So look back at my main directory on my server. I've got two things. I've got a set of directions, a motion program, and a spreadsheet to help me load data. And extract the spreadsheet and the motion program. You can read the instructions if you'd like. I'm going to walk you through using the programs. So the motion program, we can open this up in WordPad or whatever text editor you choose. Start by giving it a few variables, and we shouldn't need to write or read much actual real code. So we give it the name of the axis that we're going to move. So if we're going to be moving the x-axis, we put in x. If we're going to be moving the y-axis, we put in y. If we're doing some kind of special axis where it has a name that's more than one character, such as ATC arm for a tool changer, this needs to be in parentheses. Anytime we get more than one character, must be in parentheses, otherwise the program will fail. This is a setting to check to make sure the machine is in the right units, true or false. Creatively, we give it the start position where we want it to start. We give the end position. You'll notice this says millimeter inch degrees, meaning that enter in the units of the axis you're working in. If you're working in metric, this would be 10 millimeters. If you're working in inch, this means 10 inch. If you're working on a rotary axis, this means 10 degrees. So it's based on the context of what kind of axis are you working on. Same for the end position. Where do you want to stop? What's the distance between steps? So this is a pretty silly example of going from 10 to 30. The steps of 10, so let's change that to 1 millimeter steps. How much time should we dwell between each step? It takes a little bit of time for the laser to register a point, so this is a dwell and allows the machine to wait for us. What feed rate should we use when we're moving between steps? We can enter that here. Again, that's based on the context of the axis. Are we doing it in millimeter per minute, inch per minute, or degree per minute? We always have to get to the start point. If we're using something fairly slow as our feed rate between points to keep the machine from oscillating too much, Maybe we want to just truck on over to the start point, just get there and get started. This is especially useful on very large machines where you may have a 5 meter, 15-foot bed, something like that, where you want to just get to the start. It's a very common thing where we'll move the machine from some point before the starting position through the range of motion and then go a little bit past the end of travel. This allows the machine to move always in the same direction. We can take up any backlash or slop, so we can use this overshoot move. In this case, this would mean start 0.050 behind the first point. In my case, that would be 50 micron, which is probably too small since I'm working in metric. Something closer to 200, 300 micron might be more appropriate. This says 50 thou, but this is an allowance in the part program that's built in and ready for you to use. The next section is some custom code. There are certain machines out there where, for example, if the spindle is not moving, the machine will not allow you to execute a G1 move. So in a case like that, we could do something like throw in an M19 or a S10 M5, something like that, just to get the spindle moving so that we don't run into limitations where the control is trying to protect us. We could put in other things here like G500. We could put in trafo off. Anything that needs to be done as custom lines of code, throw it in here. The reason that there's a special entry point for custom lines of code is the next line. It says, no more user stuff below here, all code. In anything resembling a normal circumstance, there's no reason for you to go beyond this line. If we look at the cursor over on the right-hand side, we've gone through maybe a fifth of the program compared to how much is actually there. The rest of this is just going to take the information you've typed in, which is the things which are relevant to making the machine move, and it's going to run through a loop and make the machine move. The exception to the rule of no more user stuff below here, all code, is that occasionally there will be problems with soft limits on the machine where we're trying to move inside or outside, obviously outside, a soft limit. There's a set of checks here for soft limit faults that sometimes are a little bit overkill, and this doesn't really protect the machine. The reason that these checks are in here is that, especially on very long axes, moving through a whole range of motion of the axis may take 5 or 10 minutes. It's very irritating to get through 3/4 of the points to find out that, oh, we've got an error with the last 2 points that we didn't know about. This is a way for the program to check before it starts that where it shouldn't exceed a soft limit on the far end. If this is problematic, just comment out the lines that are stopping you. So once we have this, I'll hit save. This is my Motion 1.4 program. I changed my axis name to ATC ARM, which is obviously not going to work on my machine that only has 4 axes. So I'll change this to X. This program's already on my file server. So I'll connect to my machine again. Program Manager. Go find my motion program. Execute. Cycle start. And in the header, it's going to tell us where is it going to move every time it's going to do something. So as promised, I had that 50 micron overshoot move. I'm starting 50 micron before my starting point of 10 millimeter. If we want to look at the program again for quick comparison. I've got starting position at 10 millimeter. I set true for using an overshoot move, 50 micron, doing exactly as promised. So it moved to our start position, tells us it's at the overshoot position. Cycle start to move to the first point. Now we're sitting at the first point. This is where we zero or tear the laser. And it's waiting for a cycle start, as it tells us. Press cycle start, it moves to X11 because I've got a step size of 1. I've got a fairly fast dwell here of 1 second, which is a little bit fast for the real world, but for watching videos on the internet, fast enough. So this program is going to continue on and finish. One of the things that you may have noticed in that part program is that there is no allowance for the ability to turn comp on or off in the program. That's intentional. Now, as we discussed a couple videos ago, whenever we shoot a comp run, we want to make sure that we have comp turned off. We don't want to be adding more comp to a comped machine. So to do that for ENC comp, we come into machine data, access machine data, search for 32700. We have two entries because the first entry is for measuring system 1, second entry is for measuring system 2. So we have to also pay attention to our axis. So if we're doing X, we need to turn that to a 0. In my case, because I'm working on measuring system 1, hit set MD active, then I could run this program and collect data. Now, once I've collected data and I've turned it back on, same thing, turn the comp values back on, then I can do a verification run. This has been intentionally omitted from the programs because there are many cases where special things are going on, and if this was being enforced in the part programs, it would make life more difficult than it needs to be. So now that we've done our compensation runs, we should have data in our metrology software that should be exported to a text file or a CSV or something that can be copied and pasted into a format understandable by the control. When I grab the motion program from the zip file associated with these videos, I also grab the this compensation-enc version number file. So let's open that up, because what this is going to do is this is going to allow us to enter data in the green colored fields, and it will kick out a part program in column F. To make a part program, all I need to do is copy and paste this into my text editor of choice, save it as something.mpf, load to the control, select cycle start, and the data is loaded. Now, with all these part programs I'm generating, once we've executed them a single time, all these $AAA ENC variables, these are all what are called system data. These are stored in the control, and once we run these files, they can be discarded. Some shops choose to keep the count files as a record of what have they been doing historically to see if there's been some drastic change. So, for example, if we calibrated the machine in January, everything was good, we've got a good count file, we've got that saved. We recalibrate in March because that's our schedule. Everything's good, everything's fine. We recalibrate in May, everything's fine. But then we find out that we'd somehow started making bad parts in April. What happened? We look in the comp files and we compare the March file versus the May file, and we see that all of a sudden there were some grossly different numbers. If you had kept these files, you'd be able to do that. It's a choice, not necessary. It's depending on what your shop decides to do. So let's look at the data we entered. First thing we're going to do is we're going to give it an axis name. In our case, we've been working on X, which happens to be AX1 in my case, so I'm going to leave that alone. If it was Y, I'd be entering AX2. There's a descriptive name. This is solely just for a comment to go into the part program. The control does not care about this line in any way, shape, or form, so we could say my name is Matt, and today is 27 degrees C outside. And that would be showing up in our part program. So again, for the purpose of historic data, comparing things, maybe you had a bad metrology operator and every time he shot comp on the machine, that was part of the problem. This would be a way of entering that if you're keeping that for historic reasons. Again, we're going to give it start points and end points like we've been doing. So I'm going to type in -50 to 50. And I'm going to say that I did this in steps of 10 millimeter. Again, this is ridiculously short, so it's kind of silly. The measuring system. Am I working on measuring system 1, typically the motor encoder, or measuring system 2, the direct encoder? Note that these are offset by 1, so they end up being 0 and 1 instead of 1 and 2. We punch that in, that'll update our part program. So I change that to a 1. We can see that our part program updated. Went back to 0 for all of them. We're going to skip these next two for a moment. We talked about how much memory is required for comp tables and how these need to be adjusted. The spreadsheet here is calculating a minimum value we need for the number of points for this table to go from -50 to 50 in steps of 10. It tells us we need a minimum of 11, which means that this one is not going to be able to load on our control at the moment because I only have 8 steps, so I'm going to shorten up my table. In the real world, what I would do is I would go through all my axes and punch in this rough header data of what range of motion am I using, what step size am I using. I get it to generate the number of points that I need for each axis. I'd punch all these in at once, make one archive, restore that archive, and then I only have to go through that process once instead of once per axis. So now, what I'm going to do is look at where do I enter my data for each point. Now, in the ideal world, you should be able to just copy and paste this from your metrology software. The trick is here that there are different formats lasers can give as an output. In this case, if we look at the name of the sheet is named raw, meaning raw laser data. So if we have target positions of minus 50 millimeter to 20 millimeter, I just did a simple add 0.1% to throw in some numbers here. I should have numbers that look like minus 50, minus 40, minus 30, minus 20. This is a demonstration to show you what the data should look like. You have several different formats here that are covered by different tabs in the sheet. So we also have error format. So in this example, with the default data I have going from minus 5 to 5, we should have numbers that are smallish. Same thing with compensation. We'd have numbers which are quite small. You need to pick which one of these 6 tabs matches the format that your laser is generating. If you have Renishaw lasers, either in the RTL or REN format, these are also supported, so you can copy and paste the data directly from the Renishaw software. And if you scroll off to the far right, there are some special notes about RTL files and how the Renishaw software needs to be configured to accept this correctly. You'll also notice that the RTL format, if you are using Renishaw, does an interesting thing where it stores data chronologically. So if you start from 0 and go to 100, and then come back from 100 going back towards 0, the data will go from 0 to 100 and 100 to 0, which means that when we enter the negative travel, we have to flip the data over. This is done automatically in these sheets. Similar if you're using a .ren file from Renishaw, it's directly supported from the Renishaw format. Notice that here I've got numbers like 50. One of the things I skipped earlier was that I have a multiplier in this header. The reason I have a multiplier is because the Renishaw data, if we follow the conventions laid out over here on the right, if we follow those conventions, I get data out that is in microns. So I'm able to use a multiplier here to convert microns to the millimeters that the NC needs. This is also very useful for cases where you're using rotary lasers. Most rotary lasers put out data in arc seconds, which the NC does not understand. The NC understands units of degrees for rotaries. So if you hover over the multiplier, it will also give you the conversion factor to convert arc seconds to degrees. So we're going to look at just raw data because that's the easiest one to think about. Now, in practice, what I do when I'm working on a new machine is I'll figure out which one of these I need. I'll delete all the other tabs and start renaming these as X, Y, and Z. So let's say we're going to work with raw. I'm going to say copy, create a copy, okay, create a copy, and then I will throw out all of my other files. Delete, yes. So I'll do rename, X, rename, Y, rename, Z. So X is axis 1, Y is axis 2. These are not case sensitive. Z is axis 3. And then I could enter different starting points, different ending points, so on, so on, so on. The nice thing about this is that if I've set this up for a machine in my shop, if I keep this saved as a file relative to that machine, and every time I go to recalibrate this machine, I don't need to enter new starting points, ending points, step distances. I have a record of what I've done. I just set up my laser the same way. I do the same thing every time. So we talked about the multiplier. We talked about putting in data. Again, with all these sheets, there's a little calculation here. That's only to give you something as a little bit of guidance. Throw out that calculation, overwrite the data. So let's talk about this other field that I've ignored so far, this position for zero comp. The reason that this exists is that when we set up a laser, we typically set it up at one end of travel. Now, when we set up the laser at that end of travel, we're usually going to hit the zero the laser button, or tear the laser button, somewhere at that end of travel, just like the part programs we ran a few minutes ago showed us. The problem is that may not be where we want zero compensation to be. For example, some machine builders like to use a convention where axis 0 is in the center of travel of the machine, and so you may go from minus 500 millimeter to plus 500 millimeter. Perfectly fine. They may decide that their convention says that they want to have zero comp at 0, which is in the center, but when we hit 0 on the laser, we basically shifted the no comp point to the far left at minus 500. So using that example, we go from minus 500 to positive 500, and we'll say we go in steps of 100 so it's easy to see. What this does is, and I'll just manually punch in some number. What this position for zero comp does is it reads the value where we had it 0, and then shifts all of our comp so that we end up with 0 comp at position 0. All the other data have been shifted as well. If I wanted this to have position at 0 comp at minus 500, I can do that. It's going to shift it differently. I now have 0 comp at minus 500. If I wanted this at plus 500, exactly the same. So this lets you choose where the 0 is regardless of where you zeroed your laser. So we're going to put this back to the example that we did where I ran from 10 to 30 in steps of 1. You'll also notice that you get a nag message here because I haven't updated my step size. The step distance does not match my start and end points. That's not a good thing. Change that to a 1. Follows out correctly. Now, you also notice that spreadsheet kind of fell apart. If comp at 0 shows NA, there is no data at position 21. What's position 21? Yeah, it's basically falling apart because it can't figure out where 500 is. 500 isn't in my table because I'm only going from 10 to 30. So if I set it at 0 comp at 10, everything comes back together. We've still got this bad point because I punched in a number for demonstration, so that falls more evenly now. So what I'm going to do is I'm going to take this entire column F, right-click, copy, go back to my file server, right-click, new, text document. So now I'll open this new text document, right-click, paste. You'll notice that there's a couple extra characters at the end. This is required for the NC to understand the part program. If I omit those and I leave those off, it'll give you an end of line error. But we go back up to the top. We can see all my typing errors transferred over perfectly. It's 27 degrees outside. And we get all of our comp data. So I'm going to do File, Save As. Still on my server. And I'm going to call this AX1 comp data .mpf. I also have to change this format so it doesn't save it as a TXT. I need the MPF extension. Save. Connect back to my control. And let's run this. Now we know that this is going to fail because we have the wrong number of points. Remember, we only have 8 points for our x-axis in this demo. Here's my program. Execute. It's going to cleanly fail and tell us we don't have enough points. So let's do this correctly. Hit reset. Go back to my spreadsheet. I'm going to change my step distance to 5, which means I only need 5 points less than my 8. Copy. Delete my old data. Paste. Save. Go select my program from the file server again. Execute. Cycle start. At the end, it tells me that everything was entered correctly. I need to do an NCK reset. This is a partial truth. Now, if this is the first time we're going through and loading these tables, like we saw earlier, whenever we change that header data, step size, min value, max values, things like that, I need to do a reboot. If I'm just changing these comp values, there's no reason for a reboot. Those will be effective at the end of these programs. You'll also notice that, so we don't get errors of trying to overwrite data which is already active, again, I turn comp off before we start, and all the way at the end, turn comp back on. So this table has been entered successfully, and that was out without me typing any comp numbers in. So now that we've done a complete example with ENC compensation for pitch error on a single axis, we're going to expand this into CEC compensation. This PDF we're looking at here is included in the zip file associated with these videos. There are a few differences between ENC and CEC compensation, but they're mostly expansion and not really that much of a substantial difference in terms of how we create the data. With ENC compensation, those were tied to individual axes, and the axis which was moving was the axis which was being compensated. It's very straightforward. The table is already assigned to the axis by default. With CEC compensation, we get more choices. With CEC, we're allowed to have an input axis and an output axis which are not the same. So, for example, if we're doing squareness comp, we can use CEC. With CEC, we also get to control the direction. In ENC, the same comp value is applied in both the positive and negative directions of travel. CEC allows us to have an additional variable, creatively called direction, which can have a 0, meaning behave like ENC, where the same value is applied in both directions, or it can have a -1, meaning apply it in the negative direction only, or +1, meaning apply in the positive direction only. ENC stands for encoder compensation. CEC, by the nature of being able to mix match the input and output axis, stands for cross-axis error compensation. So to look at an example of the header data for bidirectional pitch error compensation, we're going to again keep staring at the same PDF. So we have two tables that we need to create to do bidirectional compensation. We have to create one table for the negative direction of travel. We have to create one table for the positive direction of travel. Again, this is a difference between CEC and ENC, is that we must control the table numbers ourselves. They're not automatically managed for us, and they are exposed to us, unlike where they're hidden in ENC. So if we look at the negative direction of travel, that's going to be table 0 in this example. I have an input axis for table 0 of y. I have an output axis for this table of y. My direction value is -1. For the header data for the second table, table 1, is going to be y again. The output axis is going to be y again. This time I have a direction value of +1, meaning that the values are applied from this table only in the positive direction. Each of these tables can have their own set of compensation values. So if we look at the drawing, I've got my red dots scattered relative to my target points. They're not scattered the same in the positive and negative direction. We can work with this. When it comes to doing squareness compensation, this is a similar expansion of CEC. Because we're no longer limited to a single axis being part of this, I can have an input axis, being my z-axis, and an output axis as my y-axis, which means as I move z up and down, this allows me to move my y-axis. I can use this for things like squareness. I can use this for things like straightness. So to start our implementation of a set of bidirectional pitch error comp tables, we're going to go back to the zip file associated with these videos. We're going to go and find the compensation-CEC zip file. Open that up. In here we have two things that we care about right now. We have a part program for motion, and we have a compensation spreadsheet. Let's extract those. The motion program is going to look very, very similar to the one we had for ENC. Axis name, inch metric, start position, end position, step distance, dwell, feed rate, fast feed rate to get back to our initial starting point. We have an overshoot move with a distance just the same as we had before. It's possible to have more than one run with this, so if we needed to do more than one run back and forth, we can increase that number here. And just like the ENC files, if we needed to enter an M19 or a G500 or a S10M3, these are all possible here with the same line of no more user stuff below here, all code. Again, the main difference is that unlike the ENC table, this one goes out, comes back, and it's all automatic. So we're going to close that. We're not going to run that because it's just motion. Let's look at the spreadsheet. So we've got the spreadsheet open. We'll hit enable. Just like the ENC sheets, we see a lot of green fields We've got header data, we've got data enter, we've got a part program that gets generated when we're done. We also have the same 6 tabs for the different formats of data. Because this is just a demo, we're going to assume that we're working on the raw data format, and I'm going to throw out the other 5. And they're gone. So, let's look at the header data. Like ENC, we get a comment to enter who's doing the metrology work, what was the outside temperature, what's the date. Control doesn't care, but it may be part of your shop protocol. Start point, end point, and step distance, exactly the same as ENC. Table number is new. Table number is because with CEC comp, we need to pay attention to our own table numbers. We need to assign these, we need to manage them, we need to track them. Because if we load table number 0, and I load this, for example, for the x-axis positive motion, and then I reload table 0 and I load new data for the negative motion, my table 0 gets overwritten. So this is something we need to pay attention to. The base axis and compensation axis, also called input and output axis, these are where we define which axes are involved. For the case of doing a pitch error comp, the input and output axis are being the same. When I move axis 1, I want axis 1 to be compensated. The bidirectional switch here tells us what directions are we applying the compensation. If it's 0, that means no, it's not bidirectional. It means that the same values of comp are applied in both the positive and negative direction, just like ENC. If it's a value of 1, these values are going to be applied only in the positive direction of motion. If the value is negative 1, these values are going to be applied only in the negative direction of motion. So let's go ahead and make this a negative table. Are we entering numbers in intrametric? We have our 0 shift like we had for the ENC table. We're going to set this to a manual value, and this allows us to punch in a number by hand. This is going to be relevant later. We have a multiplier just like we had for ENC compensation, and then there's a special value of multiply by table. In general, this is a rarely, if ever, used value, so we're just going to leave that at 0 and not discuss it. Like ENC compensation, we also have to assign a maximum number of points for the table and allocate memory. That calculation is done here. It's machine data 18342. It's the same process of changing the machine data, making an archive, reading the archive back in. Again, this would be a case of if we're doing this in the real world, we would do all these calculations, figure out how much memory to allocate for each table, and do all of them at once. So we've decided that this is going to be the x negative table. So I'm going to now make the x positive table. So I'll copy this sheet, create a copy, move to end. I'll rename my tabs for x minus and 0 to mean that it's x minus is the real thing that I know what it is, and it's table number 0. You can use whatever names you want. X plus 1. So now we have the same starting and ending point. Even though we're going the opposite direction, I still must have a starting point that's negative and an ending point that's more positive. It always has to go from min to max. I can't have a high value in the starting point and a low value in ending point. It will not invert itself. It'll fault. So I change my table number and change my direction to 1. Change my direction to 1. And I'm done. So assuming that the numbers I had made up, again, I've just added a tenth of a percent. Assuming that those were good, all I would need to do is take my column, go to my server, make a new text file, open that up, copy and paste, everything comes in. So I'll do file, save as, table 1, or I could give it something else that's more coherent, .mpf. Come back to my spreadsheet, copy, back to Notepad, paste it in, file, save as, table 0, and we look on my file server. I've got the 2 files. Now, just like the ENC tables, all I need to do is select these and run. So now we're going to look at a common challenge that can show up when doing many runs with bidirectional comp. So let's say that we're just going to do a single run out and a single run back. We're going to look at a linear axis. We're going to call it x. So I drive from some small negative number to x0, press 0 on my laser software, drive out to x350, go a little past, come back, and on the way back when I come back to x0 from moving in the negative direction, I pick up a small comp value. That's great. And in the real world, that works just as well as it does on PowerPoint. The trick starts showing up when you start doing multiple runs. So let's say we're going to do 3 bidirectional runs, 6 runs total. The problem is that we start getting that little bit of noise from repeatability at x equals 0. So what that ends up meaning is that when we start looking at our comp values, the x0 in the positive direction, where we zero the laser, starts getting small numbers. There's 2 choices we can make. First choice is we can just ignore it and have both tables technically being correct. There's nothing wrong with them. But there'll be a small value of comp at x0 in the positive direction. For many machines, that's just fine. If for some reason that isn't fine, what we have to do is we have to make sure that we shift both tables exactly the same amount. Otherwise, what ends up happening, if we only shift one of the tables, then that doesn't pick up the correct relationship between the positive and negative directions of travel, which is the whole point of using bidirectional pitch error comp. So this isn't too big of a deal for a linear axis because most of the time we can just ignore it and it's okay. This shows up more as a problem on rotary axes. The reason it shows up more of a problem on rotary axes is that using an A-axis as an example, where we go from minus 90 to plus 90, typically before we started shooting comp with the rotary lasers, somebody had put a test bar in the spindle and they had swept the rotary axis so that we could verify that the rotary axis is properly aligned to one of the geometry axes. So they load the test bar up, they use an indicator, everything's good. If we start putting comp values in when the rotary axis is at 0, that means that we've screwed up whatever results we got with that test bar. So let's take a look at the spreadsheet and we're going to see how we can deal with this. So the first time we created the bidirectional table for X, I basically said we're going to ignore the 0 shift concept. We set it to a manual 0 shift. We set it to 0, which is, as I described in the previous section of video, we're basically just ignoring any possible error that may have shown up at the point where we zeroed out our laser. Let's look at a quick example of how we can deal with this if we wanted to shift this for X. So we've got 0 entered here. I come to my X1. I've said we're going to do an automatic shift, and I'm going to pick up 0 comp at minus 5 where we would have zeroed the laser, the far negative end. That picks up a value down here in 0 shift of minus 50 micron, because I'm working in metric, I think. These numbers are small enough and silly enough that it really becomes kind of irrelevant here. But we'll say we picked up 50 micron and shift here. What that means that I need to do is I need to go back to my other table for X, the opposite direction, the minus direction. I need to come into manual, and I need to punch in a minus 050. This will make them match. This is not necessary. I could have set both of them to manual, left both of them at 0, and I would have ended up with the same overall net results for the machine. The only difference being that with using the automatic shift and punching in the manual numbers afterwards, that means I get to control where there's 0 comp. If that's important to you, this is how you can do it. If it's not important, it doesn't matter. So what we're going to do is we're going to repeat this for a rotary axis because, as described previously, we set rotary axis 0 based on a test bar and indicators, so that does need to be corrected. Let's add a rotary axis to these tables and as tables 2 and 3, and we'll see how we deal with that. So the first thing I'm going to do is I'm going to add 2 more sheets to add tables 2 and 3. I'm going to add an A-axis. By copying some sheets. Rename them. I'm going to make A minus table 2. Do A plus is table 3. So I need to change my axis, my base axis and my comp axis. This is a bidirectional comp, so base axis and comp axis are the same. It's axis 4 for both of them. This is my plus, so I need a positive 1 there, which I already have. And I need to change my table number to 3. I'm also going to change my travel limits to minus 90, plus 90, and I'm going to do steps 45 degrees. Same thing for the A minus direction. I'm going to do minus 90 to plus 90, steps 45. Table number 2, update my axis numbers, and make this the negative table. So same kind of concept. What I need to do here is that, we'll say for my plus table, I'm going to say I want an automatic correction at 0 comp. Okay, I've got 0 comp here because, as usual, I'm cheating and adding a percent. Any percentage added to 0 is 0. So I'm just going to add some silly little number. Now, as normal, like just the same we saw in the ENC sheets, it picks up a 0 shift here. Okay, that's great. Now, this is one of those things where we can either copy this manually, or if we want to do, if you have more Excel skills and want to do a little bit trickier, we can come into A2. I can say this is a manual shift, and I can type in 0.235 like we had. Or if you're like me and you fat finger a lot of things like I just did there, I can say equals, come over to the A3 sheet, pick that, and then that's automatically transferred here. So I get my 0.235 degree offset automatically coming from here. So let's say we rerun this again 6 months later because it's time to redo the machine. So we're going to say 0.1. It automatically picked it up. We've got our part programs. Things are good. And that's the nice thing about using these sheets is that we just did a rotary axis. That was basically the same as a linear axis. There wasn't much difference. So expanding this to rotary is the only thing you really need to watch is that you need to watch your units coming out of your laser and watch this multiplier value. This is what the multiplier value was originally developed for, was linear, was for rotary axes, which output their data in arc seconds. Again, I'm going to remind you that the reason that this shows up as an effect so often on the rotary axes is because we set rotary axis 0 with the test bar and indicators. When we set up a rotary laser, we usually drive to the negative end of travel, or negative soft limit, somewhere near there. We zero the laser out there. We move all the way through the range of motion. We typically pick up a value at axis 0. If we don't shift and correct that properly, we've moved the position that we used with the test bar. So now that we've talked about doing bidirectional comp, there is also a backlash compensation per axis in machine data 32450. There's an index 0 and an index 1. Index 0 being for measuring system 1, index 1 being for measuring system 2. Again, they're offset by 1. Typically, these are applied to the motor encoder when there's no direct encoder present. Because if we apply a backlash comp on top of a direct encoder, that's not correcting for the play between the motor encoder and the direct encoder. What that's doing is that's applying an additional comp on top of whatever the direct encoder is reading. That usually causes more problems than it solves. There are some special cases where it can work, but those are very, very rare. We typically don't apply backlash comp with bidirectional CEC comp. The reason we don't use this in combination with bidirectional CEC is that bidirectional CEC already inherently has a backlash comp value built in per position. So it's already done. If it shows up where it seems like backlash comp is the right solution, this is one of those cases where go back to those offsets we talked about in the previous video and see if there's a inherent problem in the setup between your two runs and how you're shifting data. Backlash comp does not correct for the lost motion between motor encoder and direct encoder. That's more generally handled as part of friction comp and other servo optimization features. There isn't a static value that we can just punch in and say, we've got 10 micron of play in there and we need to just offset it by this much. We're going to talk about using CEC comp, cross-axis comp, to use two axes to correct for a squareness problem. Now, the above screenshot showing 110 micron per meter squareness error comes from Renishaw's ball bar software. This is one of the sample files they include, so this isn't a real machine, but it's perfectly representative of a real machine. The nice thing is that the value of 110 micron per meter showing there is actually unitless. It doesn't have a unit in intrametric. The units are 1 per a million. So all we need to do to calculate a squareness value that we're going to use in comp is we need to look at the length of an input axis, of how far does the input axis for a CEC table move. So if it's got a 2 meter range of travel from the machine data 36100, 36110, that's the soft limits. It's got 2 meters, then the answer is 2 meters. If it's 4 meters, if it's half meter, whatever it is, just look at the machine data, do a calculation. The squareness value in the units of 1 per 1 million, take the length, the squareness, multiply them together, and then divide by a million. That's all we need to do. So let's use the example of we have an x-axis carrying a y-axis, and we have this 110 micron per meter squareness value. Let's build a CEC table to take care of that error. So we're back in the spreadsheet, and we're going to implement an XY squareness table. Whenever we're doing any kind of squareness or straightness values where the input axis and the output axis are not the same, generally what we do is we're going to start with the raw laser data formatted spreadsheets. The reason we're going to do this is that there's no helper math. It's the most direct way to enter data and gives us the most control. So I'm going to start with my A3 plus table, which is table 3. I'm going to copy the sheet. So right click, move or copy, create a copy, rename it, call it XY square, and table 4 because this will be table 4. So we could put a comment in like we normally can. Starting point, we're going to work on the idea that the y-axis is pushing the x-axis. My convention is carried pushes carrying. So in reality, I end up needing to duplicate this because I have a gantry system and I'm going to have to push both sides of the gantry. But for now, we're just going to look at the single side. So we'll say that my y-axis has a range of motion at soft limits from minus 500 to 1500 millimeter. That's a 2 meter range of travel. You'll notice that I only have 2 points on my table. That's fine. I'm going to have table number 4 because table number 3 was my A plus table. My base axis, that's the one which is used to determine how much comp to push, the one that has the starting and ending point and the step distance. That's going to be my y-axis, so axis 2. My compensation axis is going to be x, so axis 1. Those are entered. Is this bidirectional? No. I want it to apply the same value in both the plus and minus directions of travel. I'm working in metric, so I'm going to leave that alone. Do I want a manual or automatic zero shift? I want this absolute manual because I'm going to be punching in numbers by hand. We want no zero shift, no multiplier, no table multiplication. So now let's take a look at our data down below. We have a leftover value from demonstrations in axis 3. And we can see that my base axis positions are minus 500 to 1500. So what is my y-axis position? And how much comp should I have in the x-axis at these y-axis positions? Theoretically, the machine should be perfectly square, so there should theoretically be no comp. In reality, there is comp, but the ideal target value should be 0. So at y minus 500, I'll punch in 0 comp. And for my x value, I'm going to make Excel do the calculation. I'll just clear the cell out, and I'll type equals. If we remember right from the previous sheet, the calculation we used is the length of travel of the input axis times the squareness value divided by 1,000,000. So I'll type length of travel, which is 2 meters, times 111.5 micron per meter squareness value divided by 1,000,000. Now this is built, our part program, based on all of that. So all we need to do is, like normal, we enter our number of points, or if we already have enough points entered, we're fine. Take our part program, execute it, do an NCK reset if needed, and we should be able to run the ball bar again and see the effects of our squareness compensation. One of the things that tends to happen fairly often with squareness compensation is that we'll enter a incorrect sign for the squareness value. So where I have showing 223 microns calculated, that may need to be a negative 223 micron value there. What we can do is, because that's not part of the header data, that's not part of your step size or your min or your max or anything important like that, we can just come into the part program, modify it, change that to a negative number, and rerun the ball bar test. This can get a little bit interesting sometimes because the Renishaw convention is based on the initial direction of travel for the plus and the negative sign, and it's also a perspective thing of which way are you looking at the XY plane. Because this can get a little bit confusing in practice, I just set it up, try it as positive, and if I'm wrong, I flip the sign, and it usually takes me less time than trying to think about it. So now we're going to talk about a few special cases. The first special case we're going to talk about is a gantry system where we have typically a long x-axis with an x1 and an x2 side. Sometimes they're called x-master, sometimes they're called x-slave, sometimes x-leading and x-following. Various different conventions exist. When we're doing any kind of ENC or CEC comp, we need to make sure that we apply comp to both x1 and x2 as my convention for naming. If we only apply comp to x1, x2 will not automatically pick up that comp value. It reads off of separate tables. So if we are going to do, for example, a compensation where we just do linear pitch error comp, I have to build one set of tables for x1, one set of tables for x2. If I'm doing bidirectional pitch error comp, that means 4 tables. 2 tables for x1, 2 tables for x2. If the x-axis is an input to a table, like the squareness comp example that we just did, where x pushes y, we only need to do that once because x is the input, not the output. Another common implementation of CEC comp is what can be called straightness or sag comp, depending on what the nomenclature you're using is. Technically, all of them are the same in terms of the tables, so the name really doesn't mean that much. The concept of straightness comp is that we have some axis moving along, and it's just a pure linear shift in the other axis. So, for example, this machine, I have a big heavy bridge. I have a big heavy ram on the bridge. The weight of the ram itself and the mast causes the y-axis to sag in the z direction as a function of y. When it's closer to the outer towers carrying the bridge, the machine's stiffer. When it's out in the middle, it's less stiff, therefore it sags more. We can use a CEC table to correct this. Back at our spreadsheet, we're going to take our XY squareness table and we're going to duplicate that and turn it into the YZ straightness. Rename it. Pretend I can type. It's going to be table number 5. So my input axis this time, assuming that Y is axis 2 and Z is axis 3, my input or base axis is going to be Y, axis 2. My output is going to be axis 3. The range limits, again, starting point, end point, that's fine. Typically when we're going to do something like straightness, this is going to be a more fine measurement than squareness, where I'm going to have more than one value. So let's say that I get values every 250 millimeter. This updates my table down at the bottom. So I've got my target value because theoretically everything should be straight, everything should always be 0. Again, I'm using the raw data sheet just like I use for squareness. And then this, for convenience, when I'm entering data, it gives me my base axis position. So when y is at minus 500, what is my compensation value for z? And I can come in and I can enter numbers here like 0.1, 0.2, so on. This is typically a case where getting data from a laser system, there are some very modern laser systems that can do this. Otherwise, it's some fairly difficult measurements by hand, so we're not going to discuss how we get the data. But as you can see, we just go ahead and we keep entering whatever numbers. And just like we built a squareness table where we have differing input and output axes, we get a sag or straightness table. Again, just like the squareness table, all we need to do is allocate memory, take the part program, run it, and CK reset if we've changed our header data from the last time we've calibrated, reboot reference, and our straightness has been corrected. There are some limited corrections we can do for other special cases. One such special case is rotation of an axis as a function of a different axis. So using the example of a gantry bridge again, let's assume that the mast is very, very heavy, causes the y-axis to sag. Not only does it pull down in z, but it also causes a rotation about the x-axis. We can do this with table multipliers. We're not going to get into the details because it's outside the scope of the videos, but this can help a little bit. It'll basically work well enough to correct to the attachment point of the head. It's very difficult to get this implemented where it has knowledge of the length of the tool. That requires some fairly hefty implementation by the OEM. It can be somewhat expanded to have a single rotary axis. If this is the case that you have, and you have a 5-axis machine, whether it be tilt-rotate head, tilt-rotate table, or some kind of mixed combination of the two, that's a point where volumetric compensation, sometimes called VCS, needs to be investigated. Using just the sag tables, some improvements can be made. It can make the machine better, but it is not as capable as VCS. We're going to talk about how inch and metric are handled with compensation tables. The good news is when it's done correctly, it's incredibly easy. When it's done incorrectly, it's horribly difficult. So we're going to do it correctly. Now, on many machines, if we come to the machine area, jog screens, auto, we get this settings button where we sometimes get a convert inch metric button right here. In this case, I'm working on completely default values, therefore I don't have this button. The existence of this button is controlled by machine data. Now, this is not a machine data that you would generally want to change if the builder has not implemented it, but this machine data 10260 controls whether or not that button is present. So I'm going to set that in reboot. And the reboot's complete. So we'll go back to the main machine page, and I get my changeover inch metric. And as described, it works. We'll notice that the machine coordinates change from inch to metric as I do this. And we'll also notice that the work coordinates are now an inch. If I go back to metric, work also changes. Now, one detail to be aware of, I'll demonstrate this in MDA, is that the machine coordinates are going to be tied to machine data 10240. If we go back, 10260 was the one that allows us to convert. 10240 is the base units of the machine. This controls the fact that right now I have my machine in metric. My machine coordinates are always going to be in metric. If, for example, I type in a G700, which is inch programming, hit cycle start, my work coordinates have toggled to inch. My machine coordinates are still in metric. My machine still is in metric, but my program is being processed as an inch program. What this means is that for the case of ENC comp, things become very, very easy. All we need to do to get ENC comp to work and be interpreted as intrametric is include a G700 for inch or G710 for metric. This is because when we convert the part programs by adding the G700, G710, all values are interpreted as intrametric based on that context. So if I programmed an X1 with the G700, that's interpreted as inch. Program X1 with the G710, that's interpreted as 1 millimeter. Same exact thing happens with the ENC tables when we do those programs. So we go back to my file server. I had my sample ENC program that we did many, many videos ago. I open this up. If I wanted to make sure that this was always going to be handled as a metric program, all I need to do is put in a G710. If I wanted to make sure that this is always interpreted as an inch program, all I have to do is put in a G700. Now all my values, like my step value, my min value, my max value, this means 50 inch, 350 inch, because I've changed the context to G700, G710. That's it. It's very easy. CEC comp is a little bit more complicated and requires a little bit more attention. Machine data 10260. That's the machine data which controls the possibility of the machine converting between inch and metric. When that value is 0, which means inch metric conversion is not possible, inch metric interpretation of the data in the tables is controlled by machine data 10240. So when we run those part programs, it's also controlled by machine data 10240. 10240 was the machine state, the machine coordinates, not the work coordinates. When machine data 10260 is 1, that means it's possible to switch back and forth between inch and metric using the soft keys, and quite a few other things also convert quite easily. When this is set, the inch metric state is controlled by machine data 32711 for the output axis of the table. What is machine data 32711? Into the control. This is a per axis machine data that says all of the comp tables where this axis is the output axis for the comp table, all that data is interpreted as metric. So let's take a look at a spreadsheet. We're back to the same spreadsheet we've been editing. Now this is just the example where we're using the x-axis as bidirectional pitch error comp, table 0, nothing special. What we'll notice is numbers entered in metric. This can be a 0 or 1. If we look to the far right here, we will have scaling system metric for axis 1. If we change that to a 0, the part program also changes. This is good for us. It makes life easy. The thing that we need to watch for is that as our comp tables start becoming more complex, and we start including rotary axes and things of that nature, anything rotary is always going to be interpreted as degrees. Thankfully, there is no such thing as an inch degree unit. But what we have to watch for is that, for example, if we have a case like this where we have some of the x-axis comp coming from table 0 and 1, where we have pitch error comp, bidirectional, and then we have some kind of squareness comp or other comp or straightness where we're pushing the x-axis based on a third table or a fourth table or a fifth table, we need to make sure that all of them are done in the same units. If we start mixing and matching units, it becomes problematic. In general, the best recommendation is to use the same units for all of your tables. If you're doing the machine in inch, do it all in inch. If you're doing it in metric, do it all in metric. Can you mix and match them? Absolutely. It becomes very difficult, very complex, and hard to keep track of your own data. I'm going to repeat something as a point of emphasis for the end users. Machine data 10260, the machine data which controls the conversion between inch and metric, is something that should generally be left alone by end users and should not be changed. The machine builder set this based on decisions that they made at some point. Now, besides the comp tables, there are other things which can be affected by this machine data. One example would be tool change positions. If the machine builder has not planned for the ability of the machine to convert between inch and metric, and you set this where it now allows conversion between inch and metric, the tool change positions and things of that nature may become incorrect. If that's the case where 10260 is 0, call your machine builder, see if it's okay. If they tell you that no, it can't be changed, the machine has to stay in metric, then the best advice is to keep all of your comp tables in metric. The value in the axial machine data, which is the same thing that the spreadsheet is using, that doesn't do anything anymore because 10260 is 0. So you'll need to do all your comps in metric. If you're in a case where machine data 10260 is 0, meaning that inch metric conversion on the control is not possible, and the metrology software you're using cannot be set to match the format expected in 10240 in terms of inch metric, one option that you have is you can use the multiplier value in the spreadsheets to do the conversion for you. So, for example, we can enter a multiplier of 25.4 into the spreadsheet, or we can say equals 1 over 25.4. This will convert only the calibration data that you've entered down in these fields here. It does not convert your header data. So let's say, for example, that we have a case where we need to do the 1 over 25.4 conversion to make this work. Again, this field becomes irrelevant because machine data 10260 is 0. We have our starting point, which was originally supposed to be minus 5. So now I will say equals minus 5 over 25.4. My endpoint will now become equals 5 over 25.4. And my step distance will become equals 1 over 25.4. You have to do 3 conversions here because we also need to convert the start and end points, make sure those are in the correct units. We can use the multiplier, and this is one way to get around limitations between the two software packages. As we've seen, there are quite a few different ways we can put together the table ID numbers to what the function is using the CEC tables. These are some examples where I've got tables 0 through 9 with 4 representative machines A, B, C, D. So if we look at A, we're going to assume that A is a gantry, and the builder has decided that this is their standard, that they're going to keep X1 and X2 paired up near the top, Y1 and Y2 following, and then followed by Z1. If, for example, they decide that this is their standard that they use across their entire product line, when they make a machine that's not a gantry, they may just go to column C and outright skip tables 2 and 3 and just not use them. That's completely and totally fine because that matches their standard. Or they may decide to use a different configuration where they decide that column B is their standard, where they keep X1, Y1, Z1 up near the top at tables 0 through 5, and start putting the coupled and following axes in tables 6 through 9. When they build a less complex machine that doesn't have the gantry, then tables 6 through 9 disappear. There are many, many, many possible ways to couple these table numbers to axes, and it's up to the builder to decide what to do. There are also end users who have decided that because they want to have a common shop standard that they tell their builder before the machine's delivered, we want the comp tables to be arranged as such and such because that is the standard as our shop as an end user. Depending on the contract, sometimes that can be done. Now, we've briefly discussed before that we can have one output axis that has many tables feeding it. This is a page from the documentation showing how the flow of tables are summed together. So if we have a single output axis here on the right, and we have compensation for it enabled, then we get a summing junction here that takes all the tables where that single axis is the output, and they get summed together. Now, this should give you an idea that in certain cases this can get complex fairly quickly. There can be a lot of data, there's a lot of decisions which have been made, there may be shop standards, there may be builder standards. How do we work backwards from an existing machine into what's been installed? The easiest way to do this is we're going to open up the files that are associated with this video. There's a program in there named CompLog that is going to help us sort this out. So let's go find the files on the file server. Here's comp log. Conveniently with comp log, there's no variables to set. We can go through the program if we want to, but because there's no choices, we don't need to. So I'm going to go back to my machine. I'm going to select comp log, and I'm going to run it. It's not going to run the first time, and that's on purpose because I'd like you to see a failure. I go into sources, comp log, execute, auto cycle start. We get messages up the top that we are logging. File is full. Increase machine data 11240. 11420 is the machine data which controls the amount of memory available for log files. So we can come into machine data. Again, it'd probably be a good idea to make an archive before we do this. I have nothing of value on the system, so 11420. I'm going to change that to 100, which is a pretty safe and conservative value. I will reboot. The reboot's done and I've referenced my axes, so let's run comp log again. We're going to see that up top it's going to throw us messages telling us it's logging table by table. If we look in the program manager, it has created a new workpiece directory on the NC for us, creatively named comp log. Each time we run comp log, it gives us a new time-stamped file and we can see it growing. So I will come back when it's done. So our logging program is finished, and we ended up with 3 log files with the same timestamp. One for CEC, one for ENC and inch, one for ENC and metric, and then we have the older timestamped one, which was the one that failed when the log file was not large enough. So let's take the 3 good files and copy them off to the file server so we can look at them. Let's go to the file server. Here's the 3 files I made. So let's look at CEC log. So we have CEC log open, and what this has done is it's given us the header data for every CEC table in the control. So if we look at this, we've got table 0 data. It tells us how many points are available in memory. It tells us, is this table enabled? It tells us, does the axis allow compensation? It gives us the input and output axes. What it also will do is it will give us things like the end position, step size, direction of the tables. If we had axes assigned as an output axis, it would be picking that up and would be throwing units on it like inch and metric or degrees, and it'd be throwing that on right here. And it's designed so that we have something that's human readable. Now what we can do with this, as we're working backwards through a machine that's already been complete, we can take this information and start compiling it in a way that makes sense to us and our own process of table 0 is the X minus comp table, its step size is blah, it runs from some limit to some other limit, and we can compile this in a way that is going to be helpful to us today. When I'm working through this, if we look, this goes from table 0 to 61, which is far down at the bottom, long way away based on the size of the scroll bar. What I normally do is that any table which isn't being used, I'll just delete that out of this for my own files, and I find it easier to work with. What we also have is we have the inch and metric copies of ENC log. Note that the timestamp for CEC log and the associated ENCs all have the same timestamp. So if we open up the metric one first, noted by the millimeter in the file name, it gives us the ENC tables, all of them in the control, with the same kind of information of how many points are available in the table, what's the table enable state, what's the start position, end position, so on, because this is the metric file. As we've been punching numbers in, we have things like my table starts at 10 millimeters, goes to 30 millimeters, goes in steps of 5 millimeters. If we go back and look at the CEC log file, we'll notice that all the values are 0 compared to the ENC values, which have numbers in them. The reason that we have numbers for ENC and not CEC is that we never actually ran the CEC part programs, we just looked at them. So we've got nice round numbers here again because this is the metric file. We created everything in metric, so nice round numbers. If we look at the inch file, we will see that we have values in inch, except now instead of being a round number like 10 millimeter, well, it's still 10 millimeter, that's just not very round in inch. So we get both data, so depending on which way the machine was configured, you can get good round numbers in either. So now let's look at this in terms of we've gone through and evaluated everything that's in the machine, and we've decided that we don't like the way that the tables are configured. Let's say that, for example, the builder had chosen to implement ENC comp for some axes, and they had chose to implement CEC comp as bidirectional for others. Let's say, for example, that we now want to convert and we want to do bidirectional for all axes. The way that we would do this is we would come into these spreadsheets and we would fill out all the header information and build up a whole set. Now, because there's going to be several reboots involved and a lot of configuration, what we'll do is we'll get the correct number of max points loaded for all the axes. We'll make the archives, we'll read them back in, which will get us enough memory for every axis. Now what we need to do is we need to do the header data for every table. So what we can do is we can come in and grab just this chunk of machine data for each table. So I'll copy that. I'll go back to my file server, create a new text document, open that up, paste in my data from table 5. Go back to my spreadsheet, go to table 4, grab just the header data. Got a few too many files open. Go back to table 3, paste that into my program, and we're building just the header data. Now, by grabbing enough of this, we're making sure that we shut off all the table enables. At the end, we can throw something like message loaded. Do that with quotes correctly. G4, F3, M2 for end of program, throw a couple of lines at the end, and this will load the header data for every table. This is convenient because now we'll have the correct header data loaded. We only need to do one NCK reset and it saves us some time. What we can also do is when we're making archives, we can also choose to make archives with the compensation data excluded. When we say create setup archive, this checkbox here controls what data is in the archive. The memory allocating machine data for comp will always be included in an NC archive. The actual comp values may not be. The reason that the comp values may be excluded is that when a machine builder is doing serial production of one machine after the next, after the next, after the next, they may not want to treat the comp values as something that gets transferred. This is a quick way for them to separate out which archives have comp and which ones don't, because you would not want to transfer the comp from one machine to the next because they're mechanically different. So now we're going to talk about the software options related to Cinemare controls. The easiest one to discuss is ENC comp because it's been included at no charge since around 2000 or earlier for most controls that Siemens has sold, including the 802 and 808 controls, the economy level controls. The CEC option was a single option for most of this time, and in about 2015 or so it split into two options. The reason that it was split is that if we're using just bidirectional pitch error comp, that required the full CEC option, which was traditionally called beam sag, which included all of the bidirectional pitch error, the squareness, the straightness, and so on. The M54 option for CEC, also called bidirectional spindle comp option, was created as a lower cost alternative to the M55 full option. The M55 full option has been available for a long time for 840D power line, 810D power line, 840DI power line, 840DI SL, 840DSL, 828 controls. Please contact your local Siemens office for more information about exactly what options are available for what control. The commercial topics change faster than the technical topics, so I'm intentionally leaving the full details out of the video. The footnote number 1 is not called out in this chart. This is available in one of the PDFs included in the zip file associated with this video. But the footnote number 1 is telling us that for CEC comp, we have a limitation of either 1 or 10 millimeter, depending on which variant of NC software is installed on the machine. There are two variants of NC software, standard and export software. The reason that export software exists is that when machines are being shipped from country to country, it's possible that the governments may get involved and there may be additional requirements in terms of paperwork, depending where the machine is going from and where it's going to. With export software, there is certain functionality removed from the NC kernel, which means that the paperwork requirements and the export requirements are generally lower because the software is less capable. Again, in the case of CEC comp, that means that the maximum value which can be applied per axis has been reduced from 10 millimeter to 1 millimeter.